Today's subject is the optimal control of a finite-state Markov chain. So I will write here the optimal control of finite-state Markov chains. Another name for this subject is Markov decision process. So it is usually represented as MDP, Markov decision process. So that in the literature, Markov decision process is more used than controlled Markov chains. And now, let me repeat again the subject that we have already studied. We are talking about the optimal. We are talking about finite-state Markov chains, which is represented by a transition probabilities matrix P of U, and then initial distribution of states that we call pi 0. And we have also mentioned an objective function, and the objective function is of the form summation. Time horizon for that one is finite, so that I will take the time starting from k up to n, and we have the incremental costs at time k depending on uk and xk. But however, I have to take the expected value of it. But before that one, I would like to change it a little bit and write this time horizon, or this summation, starting from 0 up to, say, n-1, and then add the last one, c sub n of xn there, as a function of only xn. And of course, we have to take the expected value. Okay, so that was our objective function, and we would like to minimize this objective function for this part of that course. Okay? Now, I have, say, sort of written this last one as c sub n of xn because that u sub capital N will be effective on the remaining, or at the time starting from n+1 up to infinity, but it is not included into our time horizon, so it's better to write it as c sub n of xn. Okay, now, up to now, we have learned for a given policy, a Markov policy G, we have learned how to, say, obtain the value of the objective function, but the aim is to find out the optimal G. And to explain this subject, I will first start with a very simple example. Very simple example in the sense that our Markov chain will almost be deterministic. And then afterwards, I will just say, apply the theory to a more general example, but it is still an example. And then finally, I will write the theorem. But I hope that during those examples, we will all feel what we mean by the optimal control. Okay, so that the first example that we will study is a simple one, example 1. In this example, we have 3 states of our Markov chain, and we have 2 inputs, so that our uk for any time k belongs to the set 0 and 1. The input selected is either 0 or 1. And we have to define p of 0 and p of 1. I will define p of 0 as something like that, 1, 0, 0. 1, 0, 0, and 0, 1, 0. That is certainly a probability transition matrix or transition probability matrix, but anyway, it is a degenerate one because that all the probabilities are either 0 or 1, so that corresponds to the deterministic case. And I have to define p of 1 when input is 1. That is the input, u. This is the input, u. U is equal to 0 or u is equal to 1. And this is defined as 0, 1, 0, and 0, 1, 0, and when the input is 1 and 0, I'm not sure that one, okay, I will check it later, 1, 1, 0, okay? Now, we are talking about a time horizon, a finite time horizon, so that we will choose our time horizon n, for that example, is given to us as 4. And then furthermore, we have to specify this, say, incremental costs, and the overall cost is the summation of those incremental costs that after we take the expected value. So I will certainly define the incremental costs there, but before that one, I would like to draw a diagram here to show you what happens here. Say that this is the time horizon, and this is the time k is equal to 0, k is equal to 1, k is equal to 2, 3, and the final time k is equal to 4. And at each time, we are either in state number 1 or state number 2 or 3, since we have only 3 states. So let me draw here those small circles which represents the states. So this one corresponds to state 1. State 1. That one corresponds to state 2, and this corresponds to state 3. We have 3 states, and those 3 small circles are drawn. I will write the value of the incremental cost, which is this thing, set it on those states there. So I will write here that this is equal to 4, and that is equal to 3, and this is equal to 5. Now, you may say that for which u that this corresponds to the incremental cost. And now, also in this example, we made one more simplification and assume that this c sub k of xk uk is equal to c sub k of xk alone. So it is not a function of uk, so that we have a, say, same incremental cost for each of the inputs. And then, therefore, I can write here for this time k, C0 as a column vector with 3 elements. The first one corresponds to state 1, which is 4. The second one corresponds to state 2, which is equal to 3. And the last one corresponds to the state number 3, that is equal to 5. And in the example, the other incremental costs are also given to us and written on those circles, that this is 5, and then 1 and 2. So I can write C1 as a function of the state alone, not the input, and this is equal to 5 and 1 and 2. As you can see, the incremental costs here are not stationary. I mean that they are time invariant. And for that one, we have similar incremental costs, 2, let's say, and 3, and 4. And then we have, say that these are 0, 1, and 2. And finally, at time 4, we have the incremental costs 1, 2, and 1. For example, for the last one, I can write C sub 4 as 1, 2, and 1. This exactly corresponds to this Cn there. But anyway, okay, this is a function of state alone, but all the others are also only functions of states for this special example, not in general. This is not in general true, but you can easily see that they are changing in time. They're not stationary. And now, I would like to put some arrows according to the input that we have used, using the transition probability matrices. So that I will use 2 different colors to denote the 2 different inputs there. One input is the input 0. If the input is equal to 0, I will use this red color. If the input is 0, then it says that we go from state 4 to state, from state 1 to state 1 with probability 1. So that this is the only way of, say, acting when we are here. And when we are in state number 2, then we go to state number 1 with, again, probability which is equal to 1. And if we are in state number 3, then we go to state number 2 with probability 1, which means that we are acting in, I'm sorry, this one. We are going to state number 2 with probability 1, so that this is the only way of, say, that reaching those states. And since our P matrix is invariant in time, I mean that we will apply the same P exactly for all times, that the same pattern will repeat itself. So the red line corresponds to U is equal to 0. And for the second input, I will use green lines for the second input. And for the second input, we just observe that if we are in state number 1, then we go to state number 2 according to this transition probability matrix. So from this state number 1, we go to state number 2. And if we are in state number 2, then we remain there, and this one. Now, and if we are in state number 3, I'm sorry for that one, that I just changed it. Then, if I am in state number 3, then I remain at state number 3 for the second input. And again, since the transition probability matrix is same, I mean that we have exactly the same transition for all k, that the pattern will again repeat itself, so that these will correspond to the, say, case where input is equal to 1. U is equal to 1, okay? Now, there are lots of different ways of reaching from one of those states to one of these states. A path may be like that one. Say this one, and then that one, and then this one, and then this thing, okay? If we choose this path, the total cost will be equal to, for example, that I have selected this one. That may correspond to a certain, maybe G. If I choose this path, that I will collect those numbers, 5 plus 2, that is 7, plus 3, which is 10, plus 0, which is 10 again, and plus 2, which is 12. So that we can calculate the, say, cost of every path. And then maybe we can try to find out the minimum of them. But however, of course, this is not possible, even for such a simple problem there. And we have to use a clever way of, say, computing the optimal path. I mean the optimal input sequence and the corresponding value of the objective function. Okay? And this is done by dynamic programming. And the dynamic programming is based on the fact that every part of an optimal path is also optimal. And based on that one, we will use the concept of cost to go that we have used before to obtain the optimal, say, to find the optimal input, which means optimal path, and the corresponding value of the objective function. So that will be a backwards dynamic programming, as we have done our computations backwards in the previous cases. And we just say, assume that we are here at time, or time is 4, and if time is 4, we just get exactly this cost to go values, that depends on the state. So cost to go value here is 1, and the cost to go value here is 2, since we are already at the last point, and the cost to go value there is equal to 1. So then I will write those cost to go values in this way, that this is 1, this is 2, and that is again 1. We can do nothing. But now let us assume that we are here at time 3. and we are here at that state. If we are here at that state, then we have two different choices. Either we can choose the input 0, or we can choose the input 1, so that if we choose to achieve to the last point there, if we choose, say, input as 0, then okay, here we will do some computations. If the input is equal to 0, I mean that the input at time k is equal to 0. If that is true, then cost to go from state 1 can be computed quite easily, that it will be equal to 0 plus cost to go of this function, 0 plus 1, which is equal to 1. On the other hand, if uk is equal to 1, then cost to go is equal to 0 plus this 2, 0 plus 2, which is equal to 2. And since we are trying to minimize the value of the objective function, we choose the minimum of them, which means that the selection that we made here, the optimum selection, based on the restriction that if we are here in state number 1, then choose this way. That is better. Choose this way, which means that our U3 should be equal to 1, and the overall cost to go is 0 plus 1, which is equal to 1. Because the other one will create a cost to go that is equal to 2, that is larger than 1. And we will repeat the same process for the other states. For this state, we have again said that for two different inputs, two different paths, either I can go here or I can go there. If I start from here and go to there, the cost to go is 1, and there is another 1 here, and the total of it will be equal to 2. But if I choose input which is equal to 1, then this is 1 plus 2, that is 3. 3 is certainly larger than, say, previous 2. So we just say that, okay, we have to choose this way, and write here cost to go as 1 plus this cost to go, that is 2. Okay. I'm not writing the details for that one, but when we come to this, say, time 2, I will just again write what we mean by those expressions. And for that one, we have, for this one, again we have two choices. We can either choose input as 0 or 1. If I choose input as 0, then cost to go will be the summation of this 2 and 2, which is 4. And if I choose this way, it will be equal to 1 plus 2, which is 3. So that the best way is to choose this one, and then write here the cost to go as the summation of the 2, which is 3. Okay, so therefore, our UKs are already determined. If we are in state number 1, U3 should be equal to 1. And if we are in state 2, U3, I think that I made a mistake here, that is 0. U3 should be equal to 0, and for that one, U3 should be equal to 1, because that we have selected the green line here. Okay. And now we will do exactly the same thing for time is equal to 2. When we come to this time is equal to 2, time is equal to 2, we will repeat the procedure. In other words, let us assume that state is 1, x2 is at time 2 is equal to 1, which means that we are here at that state. And then afterwards, if the input U2 is 0, then we will go along this red line, and the value that we will obtain will be equal to 2 plus the minimum cost to go there, so that it will be equal to 2 plus 1. So that the cost to go will be 2 plus 1, which is equal to 3. On the other hand, if u2 is equal to 1, then we have to follow this green line, and the cost to go will be equal to 2 plus another 2 here, that is the cost to go of that state, 2, that is 4. We choose the minimum of them. The minimum is 3. And as a result, we just say that this is the optimal path. And then furthermore, the cost to go should be equal to that 3 here. And if we are in state number 2, then again we have two choices. u2 is either equal to 0 or 1. And if u2 is equal to 0, we are in state number 2 there. If u2 is equal to 0, we will follow the red line, that the cost to go will be 3 plus 1. Cost to go will be 3 plus 1, which is equal to 4. And if we use a second input u2 as 1, follow the green line, and it will be equal to 3 plus 2, 3 plus 2, which is equal to 5. So it means that again 4 is smaller, and we choose the small one, and write here that the cost to go is exactly equal to 4, and the path that we have selected is this one. Same procedure is repeated for all times, and when we come here, that the state number 3, when xt2 is equal to 3, u2 is equal to 0, and the cost to go will be equal to 4 plus 2, 4 plus 2, that is 6. And when u2 is equal to 1, cost to go will be equal to 4 plus 3, which is equal to 7. And we choose the smallest one, that is 6, and write that that should be our path. And I put here, say that the overall cost to go is 7. Okay, I think that the procedure is quite simple. At each time, the idea here is really interesting. At each time, when we come, for example, to the time instant k is equal to 1, then we don't have to consider the remaining parts, but all we are interested in is those cost to go values which are optimally obtained. So that is the basic idea of dynamic programming. That we can forget all those, say, mess here, and just use the fact that, okay, 3, 4, and 7 summarizes the remaining part, and I have to calculate the corresponding, say, cost to go values. And when I come to the first time, then of course I will obtain, say, that achieving to the last point starting from any of those states. If only probabilities are given, then of course we have to, say, find out the expected value by multiplying the corresponding cost to go vector by the initial probabilities of the states. But anyway, let me quickly follow the procedure. For that one, we have 5 plus 3, 8, and 5 plus 3, which is again 5 plus 4, which is 9, so that this is the correct or the optimal path. And I just write here 5 plus 3, this 3 as 8. And for this one, I have here 1 plus 3 and 1 plus 4. And 1 plus 3 is better, and the overall objective value is 4. And for this one, I have 2 plus 4 and 2 plus 7. 2 plus 4 is smaller, that is 6, and I go in this way. And when we come to the first one, I have 4 plus 8 or 4 plus 4. 4 plus 4 is better, so I choose this one and write the overall cost to go as 8. I hope that I'm doing it correctly. And for that one, I have 3 plus 8 compared with 3 plus 4. And 3 plus 4 is better, so that I just put here 3 plus 4 is 7. Cost to go is 7. And for the last one, I have 5 plus 4 and 5 plus 6. 5 plus 4 is better, so that I put here 9. So what does that mean? That means that we put no restriction on this final state there. All of our aim is to reach from this point to the last one. And if we start from state number 1, then the path that we have to follow is this thing, which is shown by those arrows. And then that one. And then this one. And then this one. And as a result of that path, the cost to go will be equal to 4 plus 1, 5, plus 2, 7, plus 0, plus 1, that is 8. Okay. As another example, if I start from state number 3, then the path that we have to follow is this thing. And then afterwards, the remaining part is just same as before. And the procedure tells us what to do, how to find out, say that the optimal path, which means that the optimal input sequence if such a problem is given to us. And the idea is to go backwards and at each step solve a small optimization problem. We have a big optimization problem there, that finding the whole UK sequence, and it is sort of, say, reduced to 1, 2, 3, 4 problems, 4 small optimization problems. So that is the power of dynamic programming. Of course, solving small optimization problems, a number of small optimization problems, is much easier than solving this, say, very large problem there. Okay, now that was our first example, and on this example I have emphasized the use of dynamic programming, as well as, I hope, that the power of dynamic programming. Dynamic programming, if can be applied to a specific problem, is really an effective way of solving the optimization or the optimal control problems. It cannot be applied to all of the problems. Okay, now I will change the problem and make it not a degenerate, say, Markov chain, but right here a Markov chain, and apply the same procedure. What is the procedure? Start from the backwards, and at each time find the optimal input corresponding to every state separately. Not only one of them, but for all of them. So that is our procedure. And now I will erase this part and write the new problem. The new problem now is something like that. To keep the computations, say, simple, we have selected here a Markov chain with 2 states, and we have a P of U matrix given as, okay, I'm sorry, first I have to define what U is. U, as before, is an element of the set 0 and 1 for that example. And by the way, it is not necessary that U belongs to a finite set. We may choose, say, P of U depending on U, and U as a continuous variable, for example, between 0 and 1. This is also possible. And it really doesn't make much difference there. And however, for that one, we have selected our U again in this example. This is another example. Maybe I have to write here that this is an example. And P of U will have 2 different values. P of 0 is given as 0.7, 0.3, and 0 and 1. And P of 1 is given as 0.9, 0.1, 0.5, 0.5. We have to specify an initial condition, pi 0. Say pi 0 is 1 and 0. Okay. And we also have to specify the incremental costus and the time horizon. For that problem, the time horizon is selected as n is equal to 3. Now, therefore, we have to specify our Cn of x, which is equal to C3 of x. And this is, say, values are 0 and 6. The values of that one are given as 0 and 6. And I also have to specify C sub k of x and u for each k, I mean starting from k is equal to 0, 1, and 2. And however, for that example, we have a time invariant function for each time we have the same xu. This is really not necessary, as that example shows us. And it is given as 2u plus 1 and 4 minus u. Okay? The incremental costs are also defined, and everything is defined. Now, the problem is to find out the optimal solution, the optimal path, the optimal input sequence. Optimize what? Minimize the expected value of the summation k from 0 to 2 of C of, I do not want to write C sub k because that they are all same, of xk uk plus C sub 3 of x3, given that our x0 has a distribution, given that pi 0 here. Okay. Actually, I will solve the problem without this given condition, and at the end, I will multiply the corresponding cost to go here at time 2 with the given pi 0 in order to obtain the overall, say, value of the objective function. And you may just think that if we start from a different pi 0, then we have to obtain a different solution. Yes, of course this is correct, but however, we will obtain, say that the cost to goes for every state, not only for one of them. And as a result, the overall optimal cost will be equal to pi 0 times the value of cost to go at time equals to 0. Okay, let's see how we can solve that problem. The idea is to use dynamic programming once more and go in backwards direction. So, let us assume that k is equal to 3. K is equal to 3, which is our n. And for that one, we know the value of the objective function, or cost to go, that 0 and 6. This is cost to go. If we are in state number 1, then cost to go is 0. If we are in state number 2, the cost to go is equal to 6. And suppose that we are at time k is equal to 2. If we are in time k is equal to 2, then it was so nice to draw every u in this diagram by red and green lines, but I cannot do the same thing for that problem because that I have to calculate the expected values. So I just say choose two different u's here. That means that u2 is equal to 0 and u2 is equal to 1. When u2 is equal to 0, that means that I have to use this p of 0, and I have to use the corresponding c value there. Okay, maybe before that one, before this calculation, I should better write what c of x0 is. When u is equal to 0, u is equal to 0. That this is exactly equal to a vector. When u is equal to 0, we have 2 plus 1 that is, we have 0 plus 1 that is 1, and we have 4 minus 0 that is 4. And c of x1 will be obtained from this expression again as 2 plus 1, 3, and 4 minus 1, again 3. So we know C of x0 and C of x1 for each value of x. When x is equal to 1, its value is 1. When x is equal to 2, its value is equal to 4. When x is equal to 1, the value is 3. When x is equal to 2, the value is again equal to 3 in this incremental cost part. And now let's go back, return to this example, return to this point. K is equal to 0. I can either choose U2 as 0 or I can choose U2 as 1. Maybe I should better write here. I will draw another diagram, but including only the 2 time steps. This is the time, say, 2, and this is the time, say, 3. And we have already calculated the cost to goes for time equals to 3, and they are 0 or given to us as 0 and 6. So I will write here 0 and right there 6. And now I assume that here I am at state number 1. If I am here at state number 1, and if I apply, this is the state number 1, x is equal to 1, and if x is equal to 1, state at time 2, state is 1. And let us say that we have selected the input at this time as 0. If this is the case, then I can go, I'm just drawing this diagram for that case, U2 is 0. If U2 is 0, then I know that the incremental cost will be equal to 1 and 4. And so then I will write here the incremental cost as 1, and the incremental cost of being in state number 2 is equal to 4. And then furthermore, if I am here in state number 1, and if I am applying the input which is equal to 0, then I can go from state number 1 to state number 1 with a certain probability which is equal to 0.7. So I just write the probability here as 0.7. But I may as well go to state number 2 with a probability of, say, look at that one, 0.3. Okay, now we are trying to find out, say, that the expected value of cost to go. But it is so simple. Why? Because that if I choose, if I go in, I mean that if I am here and the input is equal to 0, then the expected value of cost to go, let us say that this is R21, okay, R21 will be equal to, at time 2, state number 1 will be equal to 1 plus 0 cost to go multiplied by the corresponding probability. That is how we calculate the expected values, 0.7 plus cost to go 6 multiplied by 0.3. So that the overall expected value will be equal to 2.8. Okay, so what is the condition? The condition here is that I am at time 2 at that state, and that I am applying the input which is equal to 0. And I can do the same thing for the second state. If I am here in the second state at time 2, and that the input that we have applied is 0, then from the second state to the second state, the probability of going from second state to the second state is 1, and the other one is equal to 0. Therefore, if the state is 2, then, and U2 is again 0, then the cost to go will be equal to 4 plus 1 times 6, that is the expected value, and which is equal to 10. So we have done a computation for U is equal to 0. Now I would like to do the same computation for U is equal to 1. Okay. for u is equal to 1, then first of all, our cost to go will change from 1 4, I'm sorry, okay, this is still say 0, 6, but however, the transition probabilities will change according, say, and it will take the values according to this matrix there. So that going from state number 1 to number 1 is 0.8, so that will be 0.89 when the input is equal to 1, and the other probability is 0.1, and for that one, the probabilities are 0.5 and 0.5. Now, we will again calculate the corresponding expected values of cost to go. And as a result, what we do, the corresponding expected values will be equal to cost to go will be equal to 1. I'm sorry, did I change this one? Yes, I have to also change that one. That this is 3 and this is also 3, since the input is equal to 1. So cost to go will be equal to the expected value of cost to go will be, if I am in state 1, will be equal to that 3 plus 0.9 times 0 plus 0.1 times 6. That is equal to 3.6. And if we are in state number 2, then the cost to go will be equal to this 3 plus 0.5 times 0. I mean that this cost to go, and 0.5 plus 0.5 times 6. That is equal to 6, okay? And now we have to make our decision. The decision is to choose the minimum of those cost to goes as before. And the minimum we have to compare, if we are in state number 1, we have to compare this, say, 2.8 with this 3.6. And we observe that 2.8 is smaller than 3.6, so that our decision UK or U2, since time is equal to 2, is equal to say that the input 0 if state is 1. And then for the other one, I have to compare this, say, 10 with that 6 here. And 6 is smaller. Therefore, U2 should be selected as 1 if state is 2. Okay, so that we made our optimal choice. So that I will put those stars there. They are the optimum inputs that we have to apply if we are in either state 1 or in state 2, depending on the state. So it's a function of the state. Now, I just want to make you remember that our input UK becomes a function of the state. Is that a function of the state? Yes, of course. If the state is 1, it is 0. If the state is, say, 2, it is equal to 1. Okay. Now we have calculated cost to goes, and we will come to the time 1. If we come to time 1, then we will repeat the procedure. Quite simple. Okay. Now, for time 2, we have calculated cost to go, the optimum cost to go. And the optimum cost to go vector there can be written for the states 1 and 2 as this one. When state is equal to 1, 2.8 is smaller than 3.6, so that we have 2.8 there. And when state is equal to 2, 10 is larger than 6, therefore we have 6 here. That is cost to go. And when we come to time, k is equal to 1, that is the time k is equal to 1. Again, we will repeat the same procedure. So let me draw the diagram here. This is the time k is equal to 1. K is equal to 1. And this is the time k is equal to 2. Maybe I should better draw here a rectangle to denote that the values that I put here are cost to go values, the optimum cost to go values. And those values, as written in the previous vector, is 2.8 and 6. And we will draw the diagram once more for two different inputs. U1, okay, U1 is equal to 0. If U1 is equal to 0, then our incremental cost, that one, is 1 for state number 1 and 4 for state number 2. And the probabilities are, that comes from this first matrix here, 0.8, 7, and 0.3. And for the other one, we have 0, or maybe I shouldn't draw this arrow here, and 0 and 1, when u is equal to 0. In a very similar manner, we can calculate the expected value of cost to go. The expected value of cost to go for that state, when u is equal to 0 at time 1, is 1 plus 0.7 multiplied by 2.8 plus 0.3 multiplied by 6. And the result is, let's see what the result is. $4.76. Okay. Does it make sense? Okay. Okay. And now for the second one, we will again do the same thing. In other words, the incremental cost is 4 plus the cost to go values are 0 multiplied by 2.8 plus 1 multiplied by 6. And the result is equal to 10. Okay. Now, for the two states, we have calculated the cost to goes when the input is equal to 0. The second diagram is for input which is equal to 1. So if U1 at time 1 is equal to 1, then we have here that those incremental costs, and the incremental costs now, when u is equal to 1, will be 3 and 3, and the cost to goes, this is the time k is equal to 1, and this is the time k is equal to 2, and the cost to goes are the values calculated before, that is 2.8 and 6. Okay. Now, to calculate the expected value, we need the transition probability matrix, and the probabilities are 0.9 and 0.1, if we are in state number 1 here. This is 0.9 and 0.1, and for the other one, we have 0.5 and 0.5. Okay. So we will repeat computation of this expected value of cost to go, when state is 1. Simple, that is 3 plus 0.9 multiplied by 2.8 plus 0.1 multiplied by 6. And the result is 6.12. Cost to go when state is 2 is 3 plus 0.5 times 2.8 plus 0.5 times 6, which is equal to, times 6, which is equal to 7.4. Now we can do our decision, we can make our decision, and that just by comparing the values of cost to go there, this cost to go value, when the input is 0, is 4.76, which is smaller than this one. So we prefer this thing, and that one is, say, or this one is smaller than that 10 here, so we prefer that one. So our decision here is that our U1 will be equal to, or U1 will be equal to 4. That is U is equal to 0 if state is 1, and U1 at time 1 will be equal to 1 if state is 2. And then furthermore, the cost to go from those two states are 6.12 and 7.4. Is that 4 point? Okay, I'm sorry. This is not correct. 4.76 and 7.4. Okay. Now we made the decision, and now we come to the initial time 0, and since we come to, now I hope that we are familiar with this procedure, so I will sort of say use as, I will not do all those analysis, but instead I will repeat it, the same procedure, by using some vectors and matrices. And what we do here, actually, when we look at, for example, this one, we have said that in the computation, the incremental cost at any time k will be added to the p of, that is a function of uk, of course, plus p of uk multiplied by cost to go at time k, at time k plus 1. Okay, that is what we are actually doing, and then once we calculate it for both of the inputs, we choose the minimum of them for each state separately. And for the last one, I will write C0 plus C0, for example, U0 is equal to 0. C0 of 0 plus P of 0 multiplied by cost to go, that is already obtained as 4.76 and 7.4. I have to calculate that one. And what is this? C0 is known, and it is equal to 1 and 4 when input is equal to 0, plus P0 is known, and it is equal to 0.7, 0.3, 0, and 1, multiplied by 4.76 and 7.4. Okay, that is the computation of cost to go for both of the states when the input is equal to 0. And the resultant vector will be equal to 6.55 approximately and 11.4. And then repeating the procedure for time 0, the input is equal to 1, we have say that the incremental cost as 3 and 3 plus the transition probabilities are 0.9, 0.1, 0.5, 0.5, multiplied by the cost to go vector 4.76 and 7.4, we will obtain the result as 8.02 and 9.08. And again, for the final decision, we will compare the two values and say that this is smaller, and compare those two values and say that this is smaller. So we have our U0 star, the optimum one, is equal to 0 if state is 1, and U0 star is equal to 1 if state is 2. And the cost to go vector is equal to 6.55 and 9.08. Okay? Now, these are the decisions. We have obtained the input U as a function of the state, as a function of the final state, so that that corresponds to a Markov policy. And then the overall value of the objective function, of course, cannot be a vector like that one, but all we have to do is to multiply this vector by the initial condition, and therefore I will write here that the optimum value is, let me write V star. V star will be equal to pi 0 multiplied by the cost to go vector there, which is 6.55 and 9.08. And if our pi 0 is 1 and 0, that is simply equal to 6.55. That is the value of the objective function optimized, the minimum value of the objective function. And I also would like to write here, I have written here V star. Actually, we have previously denoted that one as, say that V of V star maybe of, say, 1, because that this is the cost to go vector at 1, corresponding to the two states. So we have used this notation previously, or that we have used the similar kind of V values, and then finally obtained, say, that result. Now, I hope that the example is clear about how to apply the dynamic programming procedure there. But anyway, I also would like to write the overall result as a theorem, although I will not prove it. Theorem. Define recursively the functions V sub n of x is C sub n of x, and V sub k of x is equal to I, or maybe I should better write it as x is equal to I, C sub n of I from 1 to capital I, the number of states. V sub k of xk is equal to I is equal to, I will use this term infimum with respect to our u belonging to u of C sub k of x, x is equal to I I and U plus the expected value of Vk plus 1 of xk plus 1, given that xk is equal to I. Okay? This is a recursive expression that I think that we are quite familiar with, because that previously we have already written the overall objective function in this way. The only difference is to take this infimum here, that we can read it as, for us, as minimum. Okay. And this is the recursive expression. And we can say that V sub k of I is always less than or equal to some Vkg of I for an arbitrary G. That was the law that we have, that was the policy, an arbitrary policy G, and it tells us that the best thing is the one obtained by, say, minimizing the function given there with respect to U. And that is the first statement that it claims. And the second statement tells us that a Markov policy G is optimal if infimum in star, that is our star expression, if the optimum in star is achieved at G sub k of x, and then V sub k of x kg is equal to Vk star of xk star, maybe. With probability 1 and V star is equal to V0 of x0g. Expected value. The third statement, a Markov policy G is optimal only if for each k the infimum at xkg in star is achieved by G sub k of xkg. Now, actually, the two statements makes an if and only if statement. So, actually, 2 and 3 tells us that If you minimize that one, then you get the optimal way, and this is the only way of obtaining the optimum, say, solution. It's an if and only if statement. I think that's all for today.